Welcome everyone. Myself Imran Laiq from MSc Part 1, roll number 37. I am going to present a presentation in physical chemistry under the title of Competitive, Non-Competitive and Uncompetitive Inhibition. My presentation including these contents. First of all, introduction. What are enzymes? Enzymes are proteins that act as biocatalysts and catalyze accelerate chemical reaction. What are substrates? The molecules upon which enzymes may act are called substrates. And what is enzyme inhibitor? It's a molecule that binds to an enzyme and decreases its activity. By binding to enzymes' active site, inhibitors reduce the compatibility of substrate and enzyme, and this leads to the inhibition of enzyme-substrate complex formation, which prevents the catalyzation of reaction and decreasing the amount of product which produced by a reaction. History of enzyme inhibition. A scientist Michaelis viewed the different types of inhibition during his research. He determined that when the inhibitor is bound to enzyme would become inactivated, and he worked together with his friend Maud Menton on a reaction that was used to change the conformation of sucrose. And Adrien Brown and Victor Henry laid the groundwork for the discoveries in enzyme kinetics, uh, as Victor Henry made a significant contribution to enzyme kinetics during his doctoral thesis. Henry is credited with being the first to write the equation that is now known as the Michaelis-Menten equation, and Leonard Michaelis was the first scientist to distinguish the different types of inhibition by using the pH scale, which did not exist in Henry's time. Here's the types of inhibitors. Enzyme inhibitors are divided by two types: irreversible and reversible inhibitors. Reversible inhibitors are classified again by four types: competitive, non-competitive, uncompetitive, and mixed inhibition. First of all, the first one is competitive inhibition. We can see in the figure in competitive inhibition, bending of an inhibitor prevents bending of the substrate with enzyme by blocking the active site of enzyme. Here, in general representation of competitive inhibition, we can see the competitive inhibitors can bind to enzyme but not to enzyme substrate complex. Therefore, competitive inhibition increases Km but does not affect on V maximum. Uh, Here's the equation for competitive inhibition. Competitive inhibition increases the apparent value of the Michaelis-Menten constant such that initial rate of the reaction is given by this reaction. In the simplest case of the single substrate enzyme obeying the Michaelis-Menten kinetic, the typical scheme is as the first equation in this slide. After adding the inhibitor, the equation becomes as the second equation in this slide. And if we assume that the system is at steady state, we will get the third equation in this slide. Okay. We know the total enzyme concentration A0 is equal to A plus ES plus AI. So from chemical kinetic, we can set up a system of equation. This equation till equation number 4. From equation 3, we can define the concentration of enzyme in terms of the concentration of enzymes substrate complex by rearranging to the Q1 into E is equal to Q minus 1 plus Q2 into ES dividing by Q1S. So we will get this equation. As in the derivation of the Michaelis-Menten equation, the term of Q minus 1 plus Q2 into Q1 we can replace the microscopic rate constant or Km. We will get the equation number 5. By substituting equation 5 into equation 4, we will get this equation. At this point, we can define the dissociation constant for the inhibitor as Ki is equal to K minus 3 upon K3. We will get the equation number 6. And at this point, substitute the equation 5 into equation 6 into equation 1. We will get the equation, and after rearranging to solve the enzyme substrate complex, we find the equation number 7 and return to our expression for V0 as we explained in equation before. So we will get the equation, this equation. And since the velocity is maximal when all the enzyme is bound as the enzyme substrate complex, so V maximum is equal to K2 into A0, replacing and combining term finally yields the convention form. We will get the equation number 8. To compute the concentration of competitive inhibition that yields a fraction of Fe0 of velocity, where Fe0 is higher than 0 and smaller than 1, we will get the equation number 9. The equation number 9 is for competitive inhibition. Okay, here's the Lin-Weaver-Burke plot for the competitive inhibition. Like I explained before, competitive inhibitor is affected on Km but does not on V maximum. So you can see in this graph, once the inhibitor is bound to the enzyme, the slope will be affected as the Km either increases or decreases, but V maximum is not changing. Okay, the second one is non-competitive inhibition. A non-competitive inhibition inhibitor binding to the enzyme and reduce its activity but does not affect the binding of substrate. From reaction, we can see the inhibitor may bind to the enzyme whether or not the substrate has already been bound. Non-competitive inhibitors have identical affinity for the enzyme and enzyme substrate complex. Here's the equation for non-competitive inhibition. Okay, here's the Lin-Weaver-Burke plot for non-competitive inhibition. According to the Lin-Weaver-Burke plot, the V maximum is reduced during the addition of a non-competitive inhibitor, which is shown in the plot by a change in both the slope and y-intercept when a non-competitive inhibitor is added. As a result, the extent of inhibition depends only on the concentration of the inhibitor. V maximum will decrease, but Km will remain the same. Okay, the third one is uncompetitive inhibition. In uncompetitive inhibition, also known as anti-competitive inhibition, we can know from the reaction it takes place when an enzyme inhibitor binds only to the enzyme substrate complex. Okay, equation for uncompetitive inhibition. The Lin-Brach equation states the first equation in this slide, and but with a higher y-intercept due to the presence of an inhibitor term, we will get the last equation in this slide. And the Michaelis-Menten equation is altered to this equation in this slide, the first equation in this slide, where we will find the last equation for uncompetitive inhibition. Here is the Lin-Weaver-Burke plot for uncompetitive inhibition. And Lin-Weaver-Burke plot for uncompetitive inhibition, V maximum and Km decrease at the same rate as a result of the inhibitor. We can see clearly in this graph. Here's the difference between all three inhibition. Competitive inhibition affected the substrate's ability to bind by binding an inhibitor and plus of a substrate, which lure the affinity of the enzyme for the substrate. But in non-competitive inhibition, the inhibitor binds to an allosteric site and prevents the enzyme substrate complex from performing a chemical reaction. And in uncompetitive inhibition is different from competitive inhibition by two observations. First, uncompetitive inhibition cannot be reversed by increasing the concentration of substrate, and second, as shown in the Linvier-Brock plot, yields parallel rather than interesting the line. Okay, here's the references from which I have prepared this presentation. And finally, I am thankful from all teaching staffs of chemistry department which helped me in completing my presentation work. And especially thanks from Vishal Skambli sir for guiding me in organizing this project assignment. Wish you all the best in your academic career. Thank you so much.